In 3.4, we're looking at some applications of determinants. And the first thing that we're going to do is look at what we mean by the adjoint of some matrix. So to remind ourselves, to do this, we're going to have to calculate some cofactors. So just reminding ourselves, if we have a matrix that's a 3 by 3 matrix, remember that the minor, each minor, comes from taking the determinant of resulting from crossing out row and column. So we would take the determinant of A22, A23, A32, A33. So that would give us minor 1, 1. And the cofactor 1, 1 is taking that minor times negative 1 raised to the 1 plus 1 power. And those come from ij, 1, 1. So in order to calculate the adjunct of A, we need to come up with what's called a cofactor matrix. And that's where we calculate each of the cofactors for that particular matrix. Then after we get each of those cofactors, we're going to transpose it, and that's going to give us the adjoint of our matrix. So let's work an example and see how this works. So let's take the matrix 1, 2, 3, 0, 1, negative 1, 2, 2, 2. And let's begin by getting the cofactor matrix and then getting the adjoint. So if we want the cofactor matrix, keep in mind when we do negative 1 to the I plus j, we're going to get a positive, a negative, a positive, negative, positive, negative, positive, negative, positive. So for our cofactor, it's going to be the same thing we get when we calculate our minor, then the opposite of our minor, then our minor. So for this one, when we calculate our 1, 1 minor, we get 2 minus negative 2, 2 minus a negative is plus, so 2 plus 2 is 4. Next one, row 1, column 2, we have 0 minus a negative 2, so 0 plus 2, and it's the opposite of that. Row 1, column 3, cross out row 1, column 3, it's 0 minus 2, so minus 2. Now if we want our cofactors for our next row, it's the opposite of cross out row and column, so 4 minus 6. Then it's the same as cross out row and column, 2 minus 6. And then the opposite of cross out row and column, 2 minus 4. And then to our last row. So it's the same as, the opposite of, and the same as. So we just need to get those numbers. So row and column, we get negative 2 minus 3. cross out row and column, we get -1 minus 0. And then cross out row and column, we get 1 minus 0. So our cofactor matrix is 4 minus 2 minus 2, 2 minus 4, 2, minus 5, 1, 1. Then if we want the adjoint of A is the transpose of that. So take this row, put it in the first column. Take this row, put it in the second column. Take this row, put it in the third column. So that's our adjoint of A. Now I'm sure you probably are thinking, why would we calculate an adjoint? Well, it turns out for any square matrix, if we want the inverse of that matrix, we can take 1 over the determinant times the adjoint of that matrix. So let's calculate the inverse of this matrix that we have. So let's copy our adjoint over. So this was our adjoint. Let's bring it over. And let's also bring A over. So A was this. So let's see if I can get rid of some of these signs. Okay, so this was matrix A. Keep in mind this is the adjoint of A, which, remember, these are the cofactors from A, but they're transposed, so these are actually the cofactors for the first row. These are the cofactors for the second row. These are the cofactors for the third row. So if we want the determinant of A, let's go across I guess we can go down the first column. So if we want to go down the first column, then it's going to be 1 times the corresponding cofactor, which is 4, plus 0 times the corresponding cofactor. And keep in mind, the cofactors that go with the first column, once they were transposed for the adjoint, are now on the first row. So times 2 plus 2 times -5. So the determinant of A is 4 plus 0 minus 10, or minus 6. So if we want the inverse of A, we take 1 over the determinant of A, so 1 over -6, multiply that times the adjoint of A, so negative times positive is negative, 4/6 or 2/3. -1/6 times 2 is -1/3. Negative and negative, there my marker goes acting up again. Oops, don't want to erase that much. Negative and negative is a positive, 5/6. The next row, we get 1/3, 2/3, -1/6. And then the next one, 1/3, -1/3, negative 1/6. So that should be the inverse of A. Now let's just copy that over and check it. If we take that times A, which I think I still have A right there. Didn't save it. So A was this. So if we multiply A inverse times A, if we did all that correctly, we should get the identity matrix. So row times column, we get 2/3, 0, 5/3. Something's not right. So this row times column, that's 2/3. Negative 1/3 times 0 is 0. 5/6 times 2, that's 10/6, or 5/3. I have a sign off somewhere. That would be 3/3, which is 1. This row times the second column. I think I have a negative off somewhere. Yeah, this was a negative. I guess when my marker went crazy, I lost that negative. So this row times the second column, that's negative 4/3. Negative 1/3. 10/6 or 5/3. So 0. And looks like if we do this row times this column, we would get 0. And just for time's sake, I'm not going to go through all of those, but notice we have the first row of the identity matrix. If we continued multiplying, we should get the next row. So that's one application of determinants, is that we can find the inverse by doing 1 over the determinant times the adjoint of that matrix. So another application is in solving systems of equations, and we briefly looked at this earlier, and it's called Cramer's rule. And if we have some system of equations, 2x plus y equals 5, x plus y equals 3, then the solution to this, if we call, let's see what their notation is, make sure. I don't know if they use the same notation or not. Okay, they use a little different. So they're going to call A, they're going to call that the coefficient matrix. Then they're going to call A1 the coefficient matrix, where we replace the first column with our result, our right side, and leave the other column. And A2, we're going to leave the first row of our first column of our coefficients, replace the second column with the right side. So it turns out that our x can be determined by the determinant of A1 over the determinant of A. Y can be found by doing the determinant of A2 over the determinant of A. So let's verify that real quickly. So if we take the determinant of A, that's easy enough. Being a 2 by 2, it's 2 minus 1. The determinant of A1 is 5 minus 3. And the determinant of A sub 2 is 6 minus 5, or 1. So x is the determinant of A1 over the determinant of A. Y is the determinant of A2 over the determinant of A, which is 1. So if we did that correctly, our solution should be 2, 1. Notice we substitute that in. 2 times 2 is 4, plus 1 is 5. 2 plus 1 is 3. So if we have a singular solution to our system of equations, x1 can be found by taking the determinant of A1 over A. x2 can be found by taking the determinant of A2 over the determinant of A. x3 can be found by taking the determinant of A3 over the determinant of A, and so forth, until we run out of variables, And remember, each A1, A2, A3, those come by leaving all columns except the nth column and replacing the nth column with the right side of the equation, the constants. So that's Cramer's rule. The other applications in this section deal with geometry. And it turns out if we want to find the area of a triangle where the triangle is described with 3 ordered pairs, that would be a Y, so if we have 3 ordered pairs in a plane, and we want to find the area of the enclosed triangle, this is our first point, this is our second point, this is our third point, then it turns out we can get the area by doing plus or minus 1/2 the determinant given by x1, y1, and then 1, x2, y2, 1, x3, y3, 1. Notice the last column. Notice we have 3 points, so we have 3 rows and 3 columns. The first 2 columns are the ordered pairs that we have. The last column is all ones. Now, without going through all the nuances, basically this arrives from recognizing that if we want this area, this is not a right triangle necessarily, and in general, the area of a triangle is 1/2 base times height, but from that triangle, it's hard to determine what is the base and what's the height. But something that's easier to determine is the area of this trapezoid, the area of this trapezoid, and then the area of this trapezoid. So if we take those first 2 areas and subtract that third area, so we add these together, and notice that has some extra stuff in it. When we take this area, we have this extra. When we find that area, we have this extra. So if we take away this area, which is a trapezoid, that'll give us the area enclosed in the triangle. And if you work through generic equations for those 3 trapezoids, it turns out that that's equivalent to this determinant. The plus and minus has to do with the order that these ordered pairs are in. Sometimes when you calculate that determinant, you might get a negative value, so you pick a sign that would make it positive. instead of doing the plus and minus, you could say, well, take the absolute value of 1/2 times that determinant. So let's look at an example. Let me just pick one out of the book. If we have the points 1, 1, 2, 4, and 4, 2, let's find the area of that enclosed region. So we're going to pick which sign we need, and we're going to do 1/2 times, put the first point in, the second point, the third point, and we're going to put all ones in that last column. So we need to calculate that determinant. So if we want to calculate that determinant, we're going to take our element times our cofactor. So our cofactor, let's just go across this top row. This will be plus, minus, plus. So our cofactor will be +1 times, cross out row and column, and we get 4 minus 2 minus 1 times our element. If we cross out row and column, we get 2 minus 4, so -2, plus 1 times, cross out row and column, 4 minus 16, -12. So inside the brackets, we get 2 plus 2 minus 12, which 2 plus 2, that's 4, minus 12, that's -8. So we need to use a negative outside. So 2 negatives make a positive. Half of 8 would be 4. So whatever we get for that, that's the area of that enclosed triangle. Now let's just briefly look at that triangle. So we had the points 1, 1, 2, 4, 4, 2. And if we were to connect those, that would be our enclosed region. Notice each one of these boxes on this grid is 1 square unit, so that's 1. If you put maybe this one and that one together, that's 2. Maybe this one and that one, that's about 3. This one and this one, roughly, that's 4. So yeah, I can see how that's roughly 4 units. And our calculation says, well, that area is exactly 4 units. So we're just using that to kind of estimate to see if that was on the right scale. So yeah, it is. Well, let's look at the case where we have points that are collinear. If we pick some points, let's pick this point, and this point. Notice if we try to make a triangle out of that, that triangle would have an area of 0 because you have no height. Or you could say you have no base. So if we run our numbers, if we say, well, our area is plus or minus 1/2 the determinant taken by doing the first ordered pair, the second ordered pair, the third ordered pair. Remember, our last column is all ones. If we take this determinant, we should get 0. So let's check that. Let's go down the third column. So this is plus minus plus minus plus. So it's positive 1 times, cross out row and column, 15 minus 20 minus 1, cross out row and column, 5 minus 15, and then the last one, positive 1 times, cross out row and column, 4 minus 9, negative 5. So inside we get minus 5 plus 10 minus 5. Minus 5 and minus 5 is minus 10 plus 10, so that's 0. And 0 times anything is 0. So yes, notice we get an area of 0. So if we calculate that and get the area to be 0, then the points are collinear. So if we take 3 points, we calculate the area of the enclosed triangle, and we get an area of 0, the points are collinear. Now it turns out we can also come up with the equation of a line if we're given 2 points by using this formula. So let's look at a graph. Let's pick 2 points. So let's just pick 2 points. Let's pick the point 2, 2 and the point 4, 3. And let's see, 2, 2, 4, 3. And we want an equation of a line that goes through there. So our area equation is plus or minus 1/2 the determinant of putting these all in, except if we don't have a third point and we want the equation, we're going to put x, y, and then 1. 2, 2, and then 1, 4, 3, and then 1. Well, in order for these to be collinear, our area has to be 0, which if we have 1/2 times the determinant equal to 0, of course 1/2 can't be 0, so that means the determinant has to be 0. Or you could say divide both sides by 1/2 and that's gone. So we want to find out what x and y would make our determinant 0. So let's calculate that determinant. So let's go across the first row. So this is positive, negative, positive. So positive x times, cross out row and column, we have 2 minus 3, so negative 1, minus y times, cross out row and column, 2 minus 4, plus 1 times, cross out row and column, 6 minus 8. And when we do that, that has to give us 0. So minus x plus 2y minus 2 equals 0. We could put this in y equals mx plus b if we wanted to, or we could just put it in standard form if we wanted to, doesn't matter. We just put it in standard form, add 2 to both sides. In standard form, we don't like a negative out front, so multiply through by a negative. I don't know how I did that. If we move 2 over, we have a plus 2 there. So change all of our signs. So that would be the equation of our line. Well, let's just verify that that goes through the points we discussed, 2, 2, and 4, 3. Notice if we put a 2 in and a 2 in, we have 2 minus 4, which is negative 2. If we put a 4 and a 3 in, we have 4 minus 6, which is negative 2. So yeah, that is the line that goes through those 2 points. And that came by recognizing they're collinear if the area is 0. Now, I'm not going to work an example out, but this can be expanded to 3 dimensions. If we have 4 points, 4 3-dimensional points, that would represent a polyhedron. Let's see if I can kind of sketch this. This is X, Y, and Z. Let's suppose we have a point here, a point here, a point here, and a point here. And actually, let's bring that out farther. Then if we connect all of these, let's see, let's make that one dotted. Then we have a polyhedron. So if we wanted to calculate the volume of that polyhedron, then we could do the same thing we did, except instead of it being area, we would have volume. Instead of being plus or minus 1/2, it'd be plus or minus 1/6. And we'd have our first order triple with a 1, our second order triple with a 1, our third order triple with a 1, and our fourth order triple with a 1. So whatever we calculated when we got that determinant, that would be the volume of that tetrahedron. If we were given 3 points instead of 4, and we wanted to find an equation of that plane, then we would leave, if points are in the same plane, think about if you have a rectangle that's 1 dimension, then that volume equals 0. Or think about it as a plane. If you have a plane, it has no depth, so the volume is 0. So if we let the first row be just X, Y, and Z, and then we fill in our 3 points in here, calculate that determinant, set it equal to 0, then the resulting equation will be the equation of a plane that contains those 3 points. Remember, to determine a line, it takes 2 points, but to determine a plane, it takes 3 points. So 3 points, that would give us a plane. So those are several applications of determinants. There are other ones that we may discuss later, but that should be sufficient for now.